Well, good afternoon, everyone. It's a distinct pleasure to introduce our WIN seminar speaker today, Professor Qing Hu, who is a full professor at the Department of Electrical Engineering and Computer Science at the Massachusetts Institute of Technology. Professor Hu is also a principal investigator in the research laboratory of electronics at MIT. Dr. Hu had his early education in China and graduated from Lanzhou University in 1981. He did his PhD in physics at Harvard. And after a postdoctoral fellowship at University of California, Berkeley, he joined the faculty at MIT in 1990. He has made a number of seminal contributions to physics and device applications over a spectrum of frequencies from millimeter microwave and terahertz to the infrared. And one of his most distinctive accomplishments has been the development of terahertz quantum cascade lasers. This breakthrough in bridging the terahertz gap, so to speak, has found applications in heterodyne receiver technology and real-time terahertz imaging, an area also pioneered incidentally by his group. Professor Hu is a fellow of the Optical Society of America, fellow of the American Physical Society, and the senior member of the IEEE. In 2009, the AAAS, that's the American Association for the Advancement of Science, awarded this distinction of fellow to 8 of MIT's most prestigious professors, including Dr. Hu, who was cited for, and I quote, outstanding contributions to the development of terahertz quantum cascade lasers and real-time terahertz imaging. So the title of the lecture today, as you see, is Terahertz Quantum Cascade Lasers and the Application. So please welcome Professor Qing Hu.
Thank you.
Could I just remind you to turn off your BlackBerry, please?
Probably iPhone too, so. Well, thanks, Professor Carty, for such a nice, extensive introduction. And it's really a pleasure to come to visit Waterloo. And in fact, the next slide, which used to be the last one, I moved to the beginning to acknowledge people. Often I would run out of time at the end of a summary and skip that part because I really do want to acknowledge one person who is a Waterloo alum. And he is instrumental in one of the applications that I'm going to talk about here, real-time terahertz imaging, namely making movies in T-rays and the real movies. It's a low budget and probably B-rated or whatever, but it's something eye-catching. So let me go to this acknowledgement first. And it took us 11 years, starting from my first paper with my late colleague Shijiao Feng in 1991 until 2002, 11 years and 3 generations of students to make our terahertz lasers. The first 2 generation students are Jürgen Smet and Bin Xu, and then the third one, Ben Williams. Under his watch, the laser was made. He's currently a faculty member at UCLA. So among those, a long list, and a couple of people I really want to highlight. John Reno is the MBE grower for this project. Without his MBE wafers, there's no way we can get anywhere close to where we are. And we have a Canadian collaboration, in fact, H.C. Liu and Zipik, and at the Canadian NRC, Professor Carty's former institute. Alan Lee is a person actually single-handedly developed this real-time terahertz imaging and also some future terahertz applications using our lasers. So this is a tongue-in-cheek slide just to wake people up in the mid-afternoon, so it's not meant to be too terribly serious. So terahertz now become really popular and kind of a hot field. And even though I've been in this field forever, ever, and we used to call even when I first went to MIT, I called it far infrared. But that was a very kind of general and abstract. People didn't really know what that far means because it depends on where you're from. And often people think 2 micron wavelengths is far infrared because 1.5 is infrared. So, one time I remember I had to argue with somebody, how far is an entirely relative concept. And coming from China, it's not Far East. I mean, that's a British perspective. So anyway, and the field of terror become really popular, and somehow maybe it sounds terrible or terrific, depends on the perspective. And then it coincides with several metrics. Teraflop computers, this is a kind of almost obsolete. Now it's really petaflop. But then terabit communication, still that's a kind of a goal to reach in WDM. And terabits per square inch magnetic memory, that's very much, essentially 100 angstrom per pitch. And so on and so forth. They all happen to be in this 10 to 12 units. And then last, but not the least, is that the US federal government. I'm glad to hear Canadian government is much more responsible. I used to put the debt, national debt here, and then the clock keep ticking so fast, so I just put, hey, deficit. So it runs every year, so constant value. Anyway, so let's put up some serious applications. At this point, there's some important, but mostly actually focused applications, not really like a large-scale commercial, killer applications, as you may think. And the terahertz sensing for gas molecules is well established. This is any molecules, small molecules with dipole moment, the rotational energy scale is in this terahertz range, several milli eV to several 10 milli eV range. So for example, OH, and this line has something to do with the ozone destruction, which I don't really quite know much about it. And NASA just sent out a satellite, part of the Earth observing system 2 years ago. And there was a heterodyne receiver to monitor this guy here at the 2.5 terahertz. That receiver, heterodyne receiver, is like your radio, and then you have local oscillator. And that local oscillator is fine for the gas source. I'm going to show a picture in my lab. Cost NASA like $22 million. So, and I can absolutely convince you this technology has been made obsolete by our new development. So chemical gas sensing, agent detection, and so on and so forth. For medical applications, this is the one thing people really work hard, and if something really can be developed, it will be always great. In fact, I just happened to talk to several people here, and and they are interested in essentially water absorbs strongly at a terahertz frequency range, and the cancer cells grow faster than the normal cells, so they have a higher water and the blood concentration. They show up in image, contrast. So if you can take advantage of that, you can really actually do some interesting stuff. The point, however, is water absorbs so strongly, and you can't really do full body penetration. Probably skin cancer on that sort will burn victims, that kind of stuff may be feasible. Explosive detection, drug detection, this is something actually being pursued very active. And I think there are promises, but I think there's still a long way to go. Biosensing, and there's interest because, the big fat molecules like DNA, the stretching mode in the terahertz range. And that modes are more specifically associated with a particular molecule rather than just, atomic spectral fingerprints. Plasma diagnosis has been a long-term customers for this fine thread technology. In long term, if you have something very compact and easy to use, very high bandwidth, short range, point-to-point communication system can be invasion. Here, let me show you this measured spectral fingerprints in the terahertz range of several common explosives done by my very close colleague, friend Xijing Zhang at the RPI. Notice those are semi-log plots. That means the vertical ones, if you do linear absorption, those features will go over the roof. All right? So those all have very distinctive features at the terahertz. So this is no joke. In fact, they have quantum chemistry simulations show those kind of rotational modes of those molecules. So one of my favorite demonstration of terahertz applications is done by this Japanese group, and Kyudo Kawase. He used to be at Riken, and now he's a professor at Nagoya. So they are doing this drug detection inside the envelope. So here he's taking advantage of the two features of terahertz: one, see-through optically opaque material, and two, the spectral fingerprints, to actually detect things inside the envelope. So here he put 3 pills inside this envelope, and the center one is the aspirin. The other 2 are illicit drugs, and which I claim have no direct experience with them. So apparently there's some problem in Japan. So you can see, and you can use this so-called TPO, terahertz OPO, to mechanically scan image and change the frequency and eventually correlate it with your database and then identify the drugs. So this is quite actually interesting and neat applications. But so far for this setup, and then this whole thing probably take almost an hour, because each image, you take probably minutes to scan, and then you have to change the frequency and do it again, and on and on. So ideally, for anything like this kind of applications, you want to be doing it in real time. So that's one thing, actually, the so-called real-time Terahertz imaging I'm going to show you is sort of working towards that goal. So this is my favorite application demonstration, which essentially spell out the requirement on both sources and detectors. For that kind of applications, you need a powerful solid-state sources with lots of power, easy to operate, and ideally it's plug and play and portable. And in order to take advantage of the spectral fingerprints, you want to have a multicolor, cover a broad frequency range. And tunable will be even better. And then if those spectral fingerprints tend to be very, very sharp, like a gas molecules, you need to actually phase lock your source and then really nail it down to be able to resolve the spectral line width, for example. And detectors, any real-time imaging, you really have to use arrays of detectors. You can't just use a single one. And that means something has to mechanically move. Okay? So having said that, and here there's this so-called Terahertz gap. Some of you may have heard about it. Some other may not. And what this refers to really, some people just say Terahertz technology is not well developed. But to me, more specifically, applies to source. Okay, so here's a collection of data point of existing technology. In addition, exclude what I'm going to talk about it. So, and there's electronic sources like transistors, frequency multipliers, and then they go up to about 1 terahertz. Notice the power drops as 1 over f to the 4th power, and I'll explain why that's the case. And there's a conventional laser diodes, and like the one I'm holding in my hand. And here, actually, it's quite easy to generate the power radiation at a high frequency, but then roll off, well, essentially it doesn't cover things below 10 terahertz. So that's the so-called Terahertz gap, and with which you can't really do much in the terahertz, both science and technology. And then I would actually explain from very fundamental level, basic level, why there's such a gap. This is something I learned years and years ago. Electronic devices work up to 1 terahertz. Photonic devices works down to 10 terahertz. As for why, nobody really give a detailed analysis until I wrote this proposal for DARPA. I have to make a comparison with all the competing technologies, and then you really have to argue why all those other technologies do not work in this region here. And actually, it comes from very fundamental physics. So regardless of the nature of the device, type of device, the generation process is all covered by Maxwell equations. There are only 4 of them, and actually quite easy to deal with. And the 2 divergence equations here only deals with static field and also polarization. Really doesn't deal with waves. And Faraday's law is a homogeneous sourceless. There's no source here. It really only deals with how wave propagates once they generate elsewhere. And really there's no source because there's no magnetic monopoles in this universe. The only equation contains source is this modified Ampere's law. Has those 2 terms. I wrote it somewhat differently. Normally you see J plus partial D partial T. So I'm break it into those 2 terms, become a lot more clear. J is so-called conduction current, and caused by movable charge carriers. And the partial P, partial T is so-called displacement current, which produced by this locally oscillating charges. And sources based on those 2 terms are electronic sources based on this J term, the conduction current, and then the photonic, so-called photonic source are based on this displacement current. And because of the nature of those 2 sources, they suffer different limitation. This guy suffers a high frequency limit, this guy suffers a low frequency limit. I'll go through with a detailed example. And start from electronic source. Let's use a BJT, bipolar junction transistor, as a prototypical example. So how this thing works, you apply AC base emitter voltage, it generates AC a collector current, and you hook that up to an antenna. And then if you design it right, as opposed to Apple engineering an iPhone 4, and then it goes out, and as a radiation. But you can see for this physical process, there are two limits. One is the transit time. It takes finite amount of time for electrons to go from an emitter to the collector. If you reverse polarity too soon, and then this process will not be completed, and then efficiency will drop. And then another limitation is RC. I mean, anyone works on electronic devices, there are always parasitic capacitance, like those two junctions. So you always charge up and discharge those capacitors, so you have RC roll off. So that means using the jargon of a microwave engineer, you have at least two poles of this system. And then above those two poles, remember this frequency here, this 2 pi is a killer. Otherwise, a terahertz gap may not exist. But this 2 pi really pretty much lower the 3 dB corner frequency by a factor of 6 or 10, roughly speaking. So that means even the tau is 200 femtosecond, very, very short. This corner frequency already below 1 terahertz. Above which, the current will drop as 1 over f squared and power drop as 1 over f to the 4th. That's what you see here. This happened not by chance, by actually a very fundamental reason here. And photonic devices, how about how that work and why that's limited? So here is a prototypical case, like the laser diode I'm holding in my hand. You have a PN diode. You apply forward bias, and you inject electrons here and the holes here. And in the space charge region here, you achieve population inversion. Okay, and then you have a gain. You can make an oscillator out of it. So, and once you can do that, it's fairly easy to generate radiation. The things I'm holding in my hand, really, no sweat to generate 10 to the 15 hertz radiation. However, as you know, quantum mechanically, you can only, in fact, the two limitations I discussed in previous slides do not apply here. One, and there is no transient issue. They're not going anywhere. They just sit at the space charge region and oscillates, that electron hole pair. Plus, they are neutral. They're not charging up or discharging any capacitance. So those limitations do not apply. And, but they can only operate above the energy gap. This is something we all know. And the smallest energy gap nature could give us is a lead salt somewhere. That's about 14 millieV, 10 terahertz, and below which really there's no natural quantum system you can actually find to do this. Otherwise, again, terahertz gap will be probably filled by using that trick. So I came actually from electronic background to build superconducting detectors for millimeter wave, submillimeter wave, 2 terahertz. And I fully appreciate all the electronic issues. And then I realized heterodyne receiver is so hard to build at the terahertz, and because RC roll off, but the LO just didn't exist. So I said, why not working on an even harder project? And then we thought hard on what to approach. Electronic approach, you have this 1 over F force. And people keep pushing a little harder, but you got a sense of how difficult that is. Photonic approach, you can't rely on natural semiconductor devices or nature-provided quantum system, but how about the artificial ones, like a quantum wells? Here, if you can grow those heterostructures, they lattice matched, and then in the conduction band or valence band, you form so-called quantum well structures. Those energy levels are called the subbands, because actually in the transverse dimension, they're continuous, just like free electrons. And the subband separation actually is determined by the well width, so you can design and grow them any way you want to make those, any frequency range you want. So that's really attractive approach. In fact, coincidentally, the year before I came on board to MIT faculty, I will mention in the chronology, Manfred Helm and Jim Allen at Belcourt, they demonstrated spontaneous emission from this guy here. I said, wow, that was really, really cool. And then I should definitely work on that, So here, actually, we're in the Institute of Nanotechnology. And let me answer the question, what does terahertz have to do with nano? Actually, it has everything to do, and based on the approach we're trying to make. So essentially, in this quantum well structure is a particle in a box. And this well width it determines the frequency or the energy separation in this fashion here. So you can see, and for 10 nanometer well width, this is 1 terahertz, and it will be about 3 nanometer-ish for 10 terahertz, as simple as that. So here, actually, this is a beautiful TEM picture taken by Zibik at Canadian NRC to show you this one of our quantum cascade structures here. You can see the 50 nanometer bar. This is about one module, which it repeats many, many times. So it really has everything to do with nano, and not we're trying to, force ourselves in. That we really rely on nano engineer and in the one dimension, vertical dimension. So, and the schematic of quantum cascade laser is essentially it's an inter-subband transition laser, and quantum cascade meaning actually is electrically injected, and the cascade is actually a very nice invention by the Bell Lab group, because here we only have electrons, not both electrons and holes involved. So electrons remain, non-annihilated. So you can use it over and over again. So one electron can emit many, many, many photons, and then really increase the power level, increase mode confinement factor, and so on and so forth. It's a very attractive, invention. So I borrowed this cartoon from Jerome Faith, who is a co-inventor of a QC laser, and his students generated this very nice one to illustrate how a quantum cascade laser works. So electrons come down, emit photons. If you notice, electrons have a smiling face, going down like a roller coaster ride, and turn pale when they reach the bottom. I think they'll probably get car sick or want another ride. So here, let me give you this a brief chronology, mostly focused on terahertz. And I don't mean to be completely comprehensive, so just want to pick some of the really important milestones. The concept was proposed as early as 1971 by Kazarov to Russian physicists in Waterloo Institute. A year after, actually, Isaki and Tsu proposed, at IBM, proposed a Bloch oscillator using superlattice. And remarkably, that Bloch oscillator is nowhere to be found these days. And because actually there's a negative dynamic differential resistance issue, but a QC laser, in really, this proposal, you can see actually, I've been working on devices for decades, and there are tons of proposals, and now mostly in collecting dust. And this is a remarkable one, reached success. Not only that, the density matrix formalism they use is still being used by us, in our group too. So it really shows actually the foresightedness of those guys. And then this is the one I mentioned, Manfred Helm and Jim Allen and Belcourt, the first saw a spontaneous emission due to inter-subband transition. In this time frame, they give Manfred give a APS March meeting, an invited talk. I was in the audience. I was totally blown away, and then took on this effort. And notice from the original proposal to the demonstration, almost a quarter of a century, finally Bell Labs group made it, and due to a lot of factors, not least the MBE growth capability, also the cascading scheme, and also the relaxation scheme, and so on and so forth. And after that, there was a quite intensive race to reach the terahertz QC laser. There's a so-called Rest-Strahlen band in semiconductor. Around the 10 terahertz is above which that's this infrared range, and below which is terahertz. You really have to go over this so-called like a hurdle. And that took 8 more years before Tratacucci's group in Pisa to finally develop the terahertz version below Rest-Strahlen band. Not because of lack of trying. We tried since our group tried since 1991. Jerome Faith's group tried hard. Capasso's group at the Bell Lab tried hard, but they're the one first came out first. And then a year later, Jerome Faith's group developed this new scheme. We developed this resonant phonon scheme. That's something I'm going to spend more time talking about. And soon after, we demonstrated metal-metal waveguide using the gain medium, which now pretty much achieve all the record. So you may wonder why it took so long to develop a terahertz QC laser after 8 years. That's a long time. And the difference between infrared and terahertz are such that I'm using this optical phonon energy in gallium arsenide, 36 millieV or 9 terahertz as a marker. Infrared, the photon energy is much, much larger. So the selective injection removal is fairly straightforward, and then you can achieve population inversion. But the terahertz is much harder, I will show, because the energy separation here is 10 millieV. It's much harder to selectively only inject electrons to 3 and only remove electrons from 2. And also, the mode confinement is much harder. The wavelengths at the terahertz is much longer, and the free carrier absorption is much stronger, so the conventional dielectric waveguide will not work for terahertz. So this is the only slide I'm going to show you a couple of very simple equations just to facilitate the discussion later. Lasing achieved, one threshold is achieved, the material gain equals to this total modal gain divided by mode confinement factor, which is a fraction of a mode inside the gain medium. And it's about 10 or 20 inverse centimeter, roughly speaking. So for inter-subband transition, actually this gain, material gain, is fairly straightforward. When you work out the quantum mechanical calculation, it really has only 3 parameters you can play with. Everything else here are fundamental constants and material properties or pi. So they're really not subject to manipulation. Here you have a population inversion, gains proportional to that. Oscillator strength, dimensionless. And that's something how strongly those 2 levels coupled radiatively. Classical Hertzian dipole involving a point charge, oscillator strength will be 1. So that's the reference point. Delta F is the line width, and then the broader line width is the smaller the peak gain is. So using the reasonable numbers, all we need is really a very modest population inversion, 3 times 10 to the 14. Give you a perspective, that's about 5% of total electron density in our structure will achieve threshold. But why it took so long? Because actually that's not easy to do. And let me actually show the schematic of an inter-subband transition. And then you appreciate some of the details. So here is a so-called intro-well scheme. And the 2 levels are in the same well. This is the easiest to understand conceptually. And then, in fact, my very first paper, essentially, I can do a back-of-the-envelope calculation of this guy here using infinite well. And so conceptually, it's easy. And there's advantages. And you have a large oscillator strength and narrow line width and so on and so forth. But the problem here is that it's not flexible. So you can see if this separation is 10 millieV, and this guy here will be very close to the bottom. And you cannot put another level 36 millieV down to use an optical phonon scattering to depopulate it. And this scheme here is interwell. And what the differences here is actually the 2 levels here are ground states in different wells. So in this case here, and the separation here is 10 millieV, but they're relative to the well, the bottom can be adjusted by the 2 well widths. You can place them anywhere you want. So you have a tremendous flexibility. You can put another ground state here, optical phonon energy below, to depopulate this guy here. And this is our approach pretty much from the very early on, but took much longer. And the disadvantage I will actually explain. You have a smaller overlap, smaller radiative transition strengths, and then broader line width. To analyze this interwell scheme, as opposed to the intrawell scheme. Intrawell scheme almost, I said, my first paper used a back-of-envelope calculation. You can almost view it as a one-dimensional artificial atom. I mean, atom, not to belittle atomic physicist. Atom is a hydrogen model with exchange energy and so on and so forth. So you can go very, very far. When you talk about this guy here, actually couples between the 2 wells. I would say it's a one-dimensional artificial molecules. And we all know, chemists know, once you generate 2 molecules, there are infinite varieties. So then the things become a lot more complicated and interesting. And then the most important thing is to discuss, to learn how those 2 levels couple as a function of the barrier width and also the relative energy position. This is something actually I learned with the first student, Jürgen Smed, and now actually I'm using this example in teaching solid-state physics when we do a tight binding model. So if you have 2 identical quantum wells far apart, called the L and the right, and you have 2 fold degenerate states, left and right have a little coupling. Okay, degenerate means energy separation is 0. Once you put them closely together with a finite barrier separating them, and then the interaction between the two will lift the degeneracy. In fact, and then you have a symmetric one, which is ground state, and anti-symmetric one, which is the excited state. This is something I learned first year in graduate school from quantum mechanics, and then we learned ground state has no nodes, and the nth excited state has exactly n nodes. We proved that from WKB and so on and so forth, and never know what's that good for here. Actually, it's right, there. So this delta naught, the anti-crossing gap, characterizes how strongly those two wells coupled. If the barrier is infinite and the delta naught is 0, like this case, they have no coupling. If a barrier is gone, and then this is ground state, the cosine, and this guy here is the sine, and delta naught will take a maximum. That will be the maximum coupling of the two. So delta naught, this anti-crossing gap, characterizes how strongly the two levels couple through a barrier. And then under a bias, here we're dealing with a artificial molecule. We can actually apply bias. And you have this so-called Stark shift. As you can imagine, this E2 will drop, and the E, let's see, one of them will, see, without this anti-crossing, the E1 will be like this, and the E2 will be like this. They will cross each other. And then, but because of the coupling of the two levels, they have a minimum energy separation, delta naught. That's why I call it anti-crossing, anti. So you can see, and as you away from this resonance, which is a minimum separation, the wave function itself actually behaves very differently. At the resonance, you have a 50-50% in two wells. They couple most strongly there. As you increase the bias, it's called the detuned. And when this separation is twice of the anti-crossing gap, you can see this wave function is mostly localized in this well. This guy is mostly localized in this well. This is called the Stark localization. A very important concept, certainly initially for me. And is delta naught characterizes how strongly the two wells couple to each other at the resonance. And then the relative detuning determines how much the coupling is reduced. That's essentially. And then you can follow my discussion about the long development. Started from a second generation BC, and we started out with the so-called diagonal transition, 3 level. All right, try to use optical phonon scattering for depopulation. And the problem here is, you can see for anyone working in this area, you recognize the line was extremely broad, almost as broad as the frequency itself. The reason is such that I'm drawing these quantum wells as ideal wells, but you grow MBE, have all this interface roughness, all this imperfection, and then that means that this level here experiences mostly this environment, and this level here mostly experiences this environment. And those two environments are not correlated, so then you got the two energy broadening add up on top of each other, you get a very broad line width. So that's non-desirable. You want a narrow line width to achieve a high peak gain. So in this second one, we did a so-called vertical design. Ben Williams already the one taking charge. So we take advantage of this understanding. If you designed one of those two levels at the anti-crossing, they lay on top of each other. So now they both face the same energetic environment. So one level goes up, the other one goes up, more or less the same. So the difference remains more or less constant. You get a much narrower line width. Okay? But the problem here is you can see there's no selectivity in terms of depopulation. If you want the lower state lifetime short, the upper state lifetime will be short too. So you have a lot of leakage current. Ideally, you want the electrons to pile up in the upper state and they always empty very fast from lower state for laser. That's the idea. So how do we go about this? And Hans Kollabor did a master thesis on this optically pumped intersubband scattering scheme. And what's remarkable is that he actually added another level in, the so-called 4 level here, and end up having a higher oscillator strength than the 3 level one. This came initially, I thought it must be a misprint typo. The reason is, and if you follow me, is that oscillator strength is proportional to the dipole moment squared. Dipole moment is the integration of these two wave functions. So you can see this guy here, the two wave functions has a very strong overlap in the same region. All right? And this guy here, however, level 3 is leaking out. Half of them are leaking out in different region, where there's no presence for level 4. So how come this guy here actually has a larger oscillator strength? really, but he said, yeah, it is correct. And actually, the reason lies in the so-called fundamental oscillator strength sum rule. Beautiful quantum mechanical. In fact, it's not even quantum mechanics. Oscillator strength sum rule comes from the fact that the eigenstate of a Hermitian Hamiltonian is a complete set. That's, here if you're dealing with a Hermitian Hamiltonian, you get a. So for this case here, you got an oscillator strings a change of sign, whether you go up or down. So here, this level 3 has someone going down, which has different oscillator strings from a sign from this guy here. So in order to compensate, to make sure the sum up to be 1, and then from 3 to 4 has to increase. That's really the origin. And then after I saw this, I said, God, we ought to try this in an electrically pumped scheme just to get more power out. If you have more oscillator strings, you get more power out. And then we try this, and then essentially within 3 iterations, we made a laser. So this is so-called a resonant phonon design. The key thing is that within the box, that's a 1 module, 4 wells, and 5 levels participate. As you can see, each well contributes 1 ground state, except this wide well contributes 2 levels, and 1 ground state and 1 excited state. We place the excited states at the optical phonon energy above, so it has very, very short lifetime. At design bias resonance, level 4, which is a lower lasing level, is anti-cross with level 3. So you can see this level here is extracted to this relaxation region. Also have very short lifetime, about half picosecond. But the level 5 is far detuned from level 3. And so it's mostly localized in this active region and has much longer lifetime. This is ideal you want to achieve. And then oscillator strength is very high, almost a unity. That's like a single point charge oscillated back and forth between those wells. And this is the key actually made our laser. And the very first one from the first wafer actually reached above a liquid nitrogen temperature. That was quite dramatic. I will comment on this quite a few more times. I came from a superconducting electronic background for millimeter wave, sub-millimeter wave detectors. I always thought that liquid helium was a way of life. I used so much, and then to get something working at the nitrogen temperature was just remarkable. I never even thought that that was the case. So now actually we're a lot more, even more ambitious. So before we had our laser, we developed this metal-metal waveguide. So let me just explain. Anyone trained in microwave engineer recognize this is nothing but a microstrip transmission line or parallel plate. And it's actually compatible with inter-subband transition rule, which E field is normal in this direction. So you can see if you can make something like this, you have almost a unity mode confinement factor, which is good. And they have many other advantages. You can use thinner, shorter, and bars. Also, metal have higher thermal conductivity than semiconductors, above 100 Kelvin. So it will be better for heat removal and so on and so forth. So easy said than done, because you can't really grow this thing in situ in the MBE. I mean, there's no way you can put gold in MBE. So you have to do post-growth and wafer bonding, and then selective substrate removal, and using edge stopper. That's what we did. And we learned from our colleagues, Professor Rive, who is our provost now, copper-copper wafer bonding for actually a 3D VLSI integration. And now you can see this is quite a good quality. And to show you some of the current record, and temperature-wise, our group held this record 186 Kelvin. Very cold in the absolute sense, but in terms of photon energy, this is actually greater. Thermal energy is greater than photon energy. It's unprecedented for any solid-state photonic devices. And I should say, because for photonic devices, if this is a photon energy, this is a KBT. For detectors, there's no way this can work because your dark current will completely overwhelm your photonic photocurrent. But the lasers, we know, is a non-equilibrium device. So the temperature itself is not really that meaningful concept. And in fact, room temperature gas laser does work in this frequency range. So KBT is far greater than h bar omega. But there, the gain medium is very, very dilute molecular gas. So if you actually increase the pressure, and then things will stop lasing, and because of collision broadening. Here, we're dealing with a solid state. And that means the electron interact with 10 to the 27 degrees of freedom. And to maintain population inversion, which is far from equilibrium, at elevated temperature is actually a highly, highly non-trivial thing. So in fact, recently, the field is struggling to go far above this guy here. There are some people arguing this poses some fundamental physical limit. And I'm arguing that's not the case. I don't believe this is a fundamental limit. It's really a psychological one. I mean, the question is, for detectors, I already mentioned, yes, this will be limited. In fact, the KT usually 10% of h bar omega. Otherwise, the dark current will be overwhelming. But not for lasers. And but empirically, there's this, all those results in this shaded area kind of follow below this, h bar omega over kb line. So except our recent work, actually almost 2 times of that. So that's actually, shows that this limit here is not a fundamental physical limit. It's just a psychological one. In fact, if we apply strong magnetic field, and then we can actually achieve much higher temperature at a lower frequency, so 225. On this chart here, actually 1 terahertz of 215 will be, over the roof. So if you're allowed to apply strong magnetic field to increase upper state lifetime, this is definitely not the limit. In fact, we can actually go down to way sub-terahertz, like 0.6 terahertz if we use a magnetic field. CW operation, for any real applications, you really need CW. So this is our record, and we haven't tried hard to break that. And so essentially, even at the nitrogen temperature, we got more than 1 milliwatt of power. That's remarkable. In a sense, you just pour nitrogen into this little dual hookup with battery, you got more than 1 milliwatt of power out. So that's coming from my background. That's really a remarkable thing. But I think that for the field, to have a much broader impact, we need to go far beyond that. To be really portable, thermoelectric cooled, or ideally room temperature. This is a new tunable device we just developed after 4 years of effort and published last year. And it's a tunable wire laser based on a totally different tuning principle. So, and I'm sketching here. This is a dispersion relation within the uniform gain medium. And like this laser structure here, kz squared longitudinal k vector, k perpendicular, and then epsilon. There's only 3 parameters you can tune to change the frequency. Okay? So all the existing tunable lasers tune either kz or epsilon. And the kz, they use external cavity to change the, this thing here. And actually, quite interestingly, all the string musical instruments tune by the same principle, kz and epsilon. They just don't use those language. So think about how do you tune violin. And you change your finger position, you change kz. Or you change the tension there, then you change actually epsilon. So far, no tunable laser or a string musical instrument to tune this guy here. For a simple reason, typically most of the lasers, the mode doesn't leak out much in the lateral direction. There's not much you can tune k perpendicular. But here, the wavelength is so long relative to our cross-section. You can see we have a huge mode here. We can actually tune by putting a plunger sideways to tune this k perpendicular. If we use a silicon, we suck the mode out. That means we reduce k perpendicular. It's a redshift. And if it's a metal, we push it in and actually increase the k perpendicular, get a blue shift. That's actually together you can get a quite substantial, like a 400 some gigahertz tuning. This is a calculated one. Took us 4 years to demonstrate this unambiguously using a quite a rudimentary thing. But since then, actually we're using MEM structure and quite a nicely developed and designed, and with the help from our colleagues. And then you can see now you can push this suspended MEM plunger close to the, the wire laser. And it's the first try, actually, already 330 gigahertz, almost 10% tuning. Remarkable, I would say. How well this works beyond my expectation. Normally, things always work below my expectation, but this is actually, we didn't even design it right. And actually, we're in the second stage redesign. I'm sure we'll get 1.5 terahertz tuning. And you can see actually those gaps, not the real gap, is due to those atmospheric absorption. Simply, we cannot measure them. And in terms of applications, one of the immediate ones, in fact, all the space scientists atmospheric scientists are dying for local oscillators in this terahertz range for terahertz heterodyne receiver. So here, in collaboration with our colleagues in Holland, and we demonstrated the terahertz heterodyne receiver using hot electron bolometer mixer. And the receiver noise temperature is 1400 Kelvin, very, very low. So I'm not going to dwell too much on it, since unless you work in this field, and you probably don't quite appreciate it. And then, but I'm going to show you some of the recent results. So this is a phase locking our laser to an electronic source. Start from 15 gigahertz, absolutely 10-digit precision signal, and then multiplied by 180 times, 180 is harmonic, to close to 2.7 terahertz with only 2 picowatt power left, and then mix with a terahertz QC laser, and then do phase locking. You can see we have this guy here phase locked, and on top, quite actually remarkable. If you zoom in, you can see this line width is 1 hertz. That's essentially faithfully following the reference. And this is one very recent that's just submitted to demonstrate this terahertz heterodyne spectroscopy of methanol. And I was talking to Professor Carty yesterday about the wood methanol, which is much better than ethanol. It doesn't use a crop. So here is the methanol. And in fact, it has many lines around this 2.9 terahertz. You have a lower sideband and the upper sideband, and then you down convert to IF. Now we can see all those lines. And really it's spectroscopy. And then we can actually change the pressure and then see the line, pressure broadening and all this fit with a theoretical model quite nicely. Really important. So let me show you some of the high power one and then the movie stuff. I promised at the beginning. High power one. This is the one thing I learned in any frequency range. If you have a fundamental oscillator, it's always much, much preferred than any nonlinear optical way of generating things. So here we have a laser fundamental oscillator. We didn't even try all that hard. You get a 250 milliwatt power, quarter of a watt. So even for CW, which is take a lot to remove heat, we get 130 some milliwatt. That's more important. This is a very nice picture to show you the contrast. And this is a fine for the gas laser, and the most powerful line is actually methanol, and at the 2.5 terahertz. And I did my PhD thesis on very similar to something to this. And you can see this is a human being here. This guy here put out the maximum 50 milliwatt. And here, our QC laser, you can't see it. It's thinner than your hair. It's about 250 milliwatt. So you get a sense. Alan Lee, the Waterloo alum, joined my group. His first project is to use this guy here to demonstrate the terahertz real-time imaging. And then since then, that was 2005, he hasn't turned it on at all, because essentially it's just too, the comparison, this is too easy to use. And once we solve the beam pattern and other issues. Incidentally, when I was a graduate student and learning how to use this thing here, and the postdoc worked with me almost get electrocuted by the CO2 laser. This guy here used the CO2 laser to pump the fine feather gas laser. He accidentally touched the ring. And at that time, I sort of, gee, if I could do something to junk this guy here, it would be quite gratifying. And that's actually how many of us can have a lifetime goal like that, can be fulfilled. That's very actually fulfilling. So we did the terahertz imaging in real time, which requires focal plane array. We borrowed this microbolometer camera, 240 by 320, more than 80,000 pixels. It's made for night vision, and designed for 10 micron wavelengths, not 100 micron wavelengths. But Alan Lee was very, very resourceful. Actually, he developed this differencing scheme, which is really neat. Otherwise, it will be mostly, you look at this camera, you will see ambient, because at 300 Kelvin, the ambient is overwhelming of terahertz radiation. So the way he did is subtract that out by synchronizing the camera with a laser. With a QC laser, we can do that easily. And fire the laser pulse at the first frame, let the second frame cool off, and take the third frame as a reference, and take the difference between two, you get terahertz here. So then you also get rid of the 1 over F noise. And then the beauty here is if you use a reflective optics, you can use the 10 micron ambient to do all the alignment, and then boom, push the button, do the terahertz radiation. So here, there's some very low budget movie made by one student script conducted and performed by one graduate student, and this Alan Lee, Waterloo alum. So on the left is this real-time movie and of a pencil made from a $100 digital camera. So nobody should be impressed by that. And on the right is a terahertz version. So you can really see through. And this is a relatively old news now. When I first showed this 2005 in the Terra Forum in Osaka, there's a room full of more than 100 people. They all do terahertz imaging. They all do the mechanical scan. When I saw this, I can hear this gasp in the audience because I don't think people at that time knew this was actually an option. So here we can actually see something inside the envelope, hidden, and with a metal cut out, and so I mean security will pull you aside, to check your stuff. And one Martin News at Bell Lab in 1995 first coined the phrase T-rays as opposed to X-rays. Not only terahertz now you hear T-rays, very catching phrase. He actually used a leaf as an example to demonstrate the hydration level. So because water absorbs strongly, so you can really see the contrast. And but then he took a gazillions of minutes. Here we just show it in the real time. And the non-invasive inspection is one of the application potentials for terahertz. In fact, we have NASA things to, in fact, after Columbia blew up, and our colleague at RPI got a lot of effort, support to do a non-invasive detection of foam attachment. So here we have this thing here, screw inside this styrofoam. So you can actually see it, and you can actually do tomography if you're clever to do a different slice. So all those applications are neat, but you could argue they can be done at using X-rays, much better quality, and probably cheaper and easier. So if you want to develop and demonstrate something new, and it has to be something that no other technology can do. And so next example, I think fits the bill. What's in it is a pencil handwritten message inside the envelope. So in this case here, X-ray will have no contrast, and infrared and optical wave cannot penetrate the envelope. Millimeter wave can, and it will show contrast, but the wavelength is too long. To resolve it, you have to focus down the tight spot, and then you do mechanical scan. So you can't do a real-time imaging. So terahertz at a 60 micron wavelengths, we can penetrate, we show contrast, and then let's see if you can decipher the message Alan Lee wrote inside the envelope. So that's the URL of this website of things on. So that's after we've done this, we realized that there's another technology can do this, namely ultrasound. But ultrasound is you have to be in contact. So here is really non-invasive and not in contact. So I mean, we definitely demonstrated something no other technology can do. There's no question for this. The question is, what's this thing good for? 20 years ago, actually, my friends from Russia said we'll definitely earn one Lenin Prize from KGB. But this is all the snooping done electronically. So nobody, maybe Japanese care about what's inside the envelope. So at this point, this kind of technology is still looking for a problem, but there's some well-defined problems like a gas sensing. So also we did real-time imaging over a standoff distance after 25 meters. This is again Alan's his work, and we know the atmosphere attenuates terahertz radiation. So here we could take advantage of QC laser's frequency flexibility. We choose atmospheric window, and then go through 25 meters still. Have a good beam pattern, can see through, some leaves. So that's So I think my time is running good. So here's some summary. I'm glad I put the acknowledgement up front. And there's some record and power, temperature. The wavelengths, actually, Jerome Faith's group held a record of 1.2 terahertz. That's 250 micron. Really, we're getting down. I'm sure if we try very, very hard, we'll get below 1 terahertz without magnetic field. With magnetic field, it's not that difficult. And the real-time terahertz imaging. And our collaborators have demonstrated a frequency phase lock. That's quite important. There are other work, actually, recently a French group demonstrated phase lock of a terahertz QC laser to a frequency cone, from mode lock laser. That's really neat, actually. And terahertz heterodyne spectroscopy. This will be the first immediate applications. There will be real customers pay real money for it. And you can argue it's not that large one, but that's, we can start it out. In the terahertz field, people keep asking me, where's the killer applications? My sense is it's a chicken egg issue. And without good tools, you're not going to have a very killer applications. And without the motivating applications, you don't have the motivation and the source to develop tools. I mean, the situation, is like this year is the 50th anniversary of a laser, invention of laser. Next year will be 50th anniversary of a diode laser. And in 1961, there are 4 groups developed the diode laser almost simultaneously. IBM was one of them. And they did the market research, and they drew the conclusion they could not sell more than 10 per year. So they gave up the field. And at that time, with that laser performance, cryogenic, 100 kiloamp per square centimeter threshold, and the pulsed low power, yes, you would remain that. Nobody could ever dream about the CD-ROM, fiber communication, and on and on. That only became possible, when the laser technology becomes much more mature and whatever. We are at that stage, probably already beyond that stage. So that's a future plans, really to make this thing here a broader impact in the future. Still unperceived applications, we need to make a source much more easy to operate. And first to maybe some electric cooler. There you really plug and play. No cryogens, no thermomechanical coolers, and ultimately really room temperature. You want something as convenient as something I'm holding in my hand. So you want the broad frequency coverage and broadly tunable. This is something I'm very happy our recent development. I think we got this. We can. I'm confident we can tune the whole gain bandwidth with this scheme, and that's 330 gigahertz, even without. Even with a design off target, that really, I think there are a lot of more to do with a broader tuning, and then you have to do an amplifier and then make it useful, so on and so forth. But I think in principle, that new tuning mechanism really works. Amplifier, this is the one thing will make things a lot more useful. As you know, oscillator, which is a laser, and useful, but limited use. Amplifier, the ones I'm holding here, and it's a lot more useful, and which essentially again without positive feedback. So that's one thing. We have a laser and we have a gain medium, and the cavity provide feedback, and then something actually not easy to get rid of that feedback because the metal waveguide has a very strong reflection everywhere, and then they always have a resonance mode. So that's something we want to work hard for both on chip. So actually we'll combine with tunable one, we'll get a high power tunable radiation out, or capture free space terahertz radiation amplified and then do imaging and processing. And several other applications, I can think of. But the bottom line is still this. This is actually very much a solid state physics transport issue. And interestingly, I I'm trained as a physicist, and took those many-body physics course as a graduate student, learned the Green's function, all the stuff, got A, then I have no idea what those things is good for. Now, actually, I'm learning those non-equilibrium Green's function formalism, along with my student, writing our own code to do this kind of stuff. It's really fun, actually. So with that, let me stop here and welcome for questions.
Thanks very much, I'm sure there'll be questions from the audience.
Okay. Any comments on this Terahertz activity? I think it's optical coherence topology.
Yeah. This? Actually, I'd rather not to talk too much about it. So this is a fairly new and involving with Alan Lee. So Alan Lee and I, we just formed a commercial entity. Wants to, I mean, OCT, you know, is essentially measure the depth. So we want to do that terahertz using and then the depth resolution is inversely proportional to bandwidth, and that's this thing comes in to play. That's as much as I would like to say here.
Next, someone. Yes.
What's the difference between you have used the microlumbar camera for the imaging? What's the difference between this kind of camera and infrared camera?
What's the difference? Actually, it's the same camera. We just took it without any modification. So is that what you mean?
Is it infrared camera?
Yeah, it is infrared camera. So, and it can be modified not without too much effort to make it much more sensitive to terahertz radiation. In fact, I was doing consulting with the BAE Systems, and that's the camera we borrowed from. And I know they were working on mid-wave infrared camera by coating this guy here with a different semi-metal, which absorbs strongly at the terahertz as well. That's what I had in mind. But we're never able to get one. So we just got this, they call it the night vision one for 10 microns. So essentially, the energy absorber are the silicon nitride and also the VOX. They absorb strongly at 10 microns. At the terahertz, Alan did the measurement is about the 4% optical efficiency at the 4 terahertz. Will be much lower at the even longer wavelengths. So, but still, that's the movie you saw.
I'm from Silicon community, so I have no idea about the phonons in gallium arsenide.
Okay.
But what I could understand is that you have level 3 to 1, and you prefer that you populate electrons from 2 to 1
right.
by LO phonons.
Right.
So what the difference between 3 and 2 is small is comparable with acoustic phonons. Do you mean that here acoustic phonons is not important?
No. That's it's a very good question. No, actually, if you come from silicon background, especially working on a fashionable band-to-band tunneling diode, there acoustic phonon is the whole thing, is everything. Because acoustic phonon there is several 10 millieV and also cover whole brilliant zone. And but not here, because all the scattering here happen in conduction band and very close to the gamma point. So essentially, acoustic phonons, Hamiltonian has a Q, the phonon momentum. So it has a very little phonon momentum. So this scattering time for acoustic phonons is like a nanosecond. So by all the practical purposes, our optic phonon here, we calculate here half picosecond. So impurity interface is much, much stronger than acoustic. This is one thing when I talk with my colleague about the band-to-band tunneling transistor, and I said, what about the impurity? They said, no, that's not the issue. And here is the opposite, because there, band-to-band, it's from gamma to L, right? Or in silicon, and essentially it's a huge Q.
So because of huge Q, we have
the larger scattering.
Energy
Yes.
which comes
Right. Yeah, the Hamiltonian is a proportional to Q. So not here. Yeah.
Thank you.
Well, good question. I mean, really come from different field. You have a different sense of your parameter environment, and then somehow you have built-in bias. And then, but it's good to talk to people from different fields and you realize, That's
you talked about terahertz amplifiers. Do you envision them being used in communication along with terahertz lasers?
Well, terahertz communication free space is something. This is something actually interesting. DARPA, when they first started this in 1999, they used free space communication as a motivation, but I haven't heard anything. I mean, the idea is, atmosphere will block all the radiation. Nobody can eavesdrop it. I don't have that in mind because I don't know a customer. So if there's one, certainly, yes, the amplifier would be helpful, but certainly source will be first. But there's fairly sensitive detectors if you can live with a liquid helium. I mean, that's my background. Superconducting detectors can be quite sensitive. So here, what we're trying to do is a couple of things. Immediate things actually make a MOPA. Multiple master oscillator power amplifier combined with this guy here. Remember that the tunable wire laser teeny tiny, and you can imagine it does not generate much power. And in order to make it useful, you have to attach to an amplifier. That would be the first step. And then if we do that, and then we try to amplify T-rays from free space for imaging initially. That would be actually then you have room temperature detector, have a lot more sensitivity. That's
for the imaging thing in the envelope, when you read whatever was written.
You want to read the message again?
Yeah, the message. Yeah. I suppose it was written by ink, right?
Sorry?
I suppose it was written by ink, not by pencil.
No, by pencil actually. No. You actually you try to no. It's not the wet. It's a pencil. It's absolutely dry. It's not the. I mean, I no water will definitely show up the contrast. So in this case here, it's a pencil, and I saw it. And in fact, I was joking about it. We did this in 2005, just right after graphene took over. Otherwise, I could see real-time imaging of graphene flakes, whatever. So it's a dry thing. I mean, if let me see. Alan did a laser printed message. I don't think he saw a good image. So that's, I mean, it really depends on the material. I think the contrast is probably just the carbon, whatever.
So did you try it on the dry ink? So that's carbon. So the absorption is coming from the carbon. Did you try it on the dry ink?
I don't remember. I remember he tried on laser printed one. It wasn't very good.
It wasn't.
Yeah. So I mean, probably carbon or maybe indentation. Well, I don't think indentation. You need some index contrast. So, I don't know. We basically he did all those I mean, for fun pretty much. I mean, there's no customer knocking on our door. Otherwise, we'll really zoom in on those stuff. So he basically just did it. Say we can do this. So then.
I have a question regarding the fundamental limit that people think that it would be for the sources.
Mm-hmm.
I think it doesn't make sense to put any fundamental limit on that. In terms of the detector, when you compare H bar omega to KT, that makes sense because you are dealing with the energy of the photon.
Right.
You're trying not to wash it out with the fluctuations. But in the source part, you're dealing with the reciprocal phenomena. So basically, the KBT is putting some kind of bandwidth around the photon that you're producing. Mm-hmm. So I'm trying to understand why people think that there is a fundamental limit.
No, I don't. I agree. No, there's no fundamental limit. However, you hear that kind of I call it noise being said, and then that's why I'm the one really making this sticking my neck out, to debut such a claim, because we had our first laser 2002, and then within I think within half a year we reached 137 Kelvin. And I remember I gave this plenary talk at the IR millimeter wave conference in 2003. I said that within a year we'll get to 200 Kelvin. At that time, we didn't even have a CW laser. I thought that's much harder. And it took us from then to now, and still, actually, where is it? I forgot. Took us so long, 186 Kelvin. So we are in the progress like several degrees per year almost. And then people started really making, and also, my former student, postdoc Ben Williams, this review article, just empirically gather those data, it seems to follow this, you know, h bar omega thing. And yeah, here. You can see actually this shaded area. That's all those data. Okay, and then you have some highlight here.
That might make sense for the detectors, but
Yeah,
not.
yeah. No, I don't believe. I don't believe there's any fundamental limit. On that hand, people take this, and some even influential ones, and then they will somehow try to influence where the resources are being located. And then instead of this approach, which I believe still the one hold the key to some other approaches, they can demonstrate room temperature but teeny tiny amount of power. So that's, yeah. No, I don't believe it. That's the whole slide. You can see my opinion is unequivocal.
So can I have one follow-up question?
You're running into your own time, remember?
Oh, okay. So actually, when you showed the spectrum of the terahertz laser that we got, it's really old. And of course, when you are making the laser, so you have to filter out the spectrum that you don't want. So I haven't seen anything on that part from your talk. So to just address that, how you make that filtering and you.
Oh, okay. Yeah. Sure. Yes, our gain medium, the gain bandwidth is really broad. In fact, you're absolutely right. I'm sure at least 1 terahertz, which is good now. Actually, we can take advantage of that, do a very broad tuning.
The calculation that you have done is based just on the dipole moment calculation,
right?
Related to the physical structure,
right?
Right. So I'm just asking that the bandwidth of the terahertz.
But
the photon that you're getting is coming from the dipole moment calculation, nothing related to the structure.
Well, I mean, there are two things. So there's a gain bandwidth, and there's a spontaneous emission I showed before, like a terahertz. And then the laser line width, I mean, we demonstrated the one phase lock is below kilohertz. In fact, we need that for, and that's a Charlotte-Towns limit to spectroscopy. As for why we have such a narrow line width, usually when you do Fabry-Perot, and they have multiple modes, but I mean, this is a one well-developed. You can use the DFB to select it. Yeah, so here actually show you some picture of, this is the second order DFB for surface emitting. So then you get a very single mode, robust single mode. So that's all those games being played by diode community for decades and decades. So
well, I think we better finish off there and move on. I hope, ladies and gentlemen, that you will agree with me that Professor Hu has given us just a tremendous and beautifully illustrated talk this afternoon, demonstrating not only his deep fundamental understanding of the underlying principles for terahertz quantum cascade lasing, but also how innovative his group has been in implementing these lasers in semiconductor nanostructures. So thank you very much. It was really
okay. Well,
nice to have you here.
Well, thanks for your attention. So.